Three planets, three dramatic headlines, a lava world with an atmosphere, a possible ocean world linked to life, and a giant planet where alien sunlight manufactures sulfur dioxide. All three stories begin with real JWST data, but they do not all end with the same level of certainty. To understand what the telescope actually discovered, we need to climb an evidence ladder, one rung at a time, and notice exactly where measurement becomes interpretation. Start at the bottom of that ladder with photons. JWST does not take a close-up photograph of an exoplanet's weather. For these worlds, it measures tiny changes in infrared light. During a transit, some starlight filters through the thin edge of a planet's atmosphere. Different wavelengths are absorbed by different combinations of gases, leaving a transmission spectrum. In thermal emission observations, the planet's own infrared glow is measured, and its brightness can be compared with models for a bare surface or an atmosphere. Those detector counts become a calibrated spectrum. The spectrum contains features. Retrieval models test which molecules and abundances can reproduce those features. Chemical models ask how those molecules could form. Only after all of that do we reach the big planetary story: an atmosphere, a climate, an ocean, or life. Every rung can be scientifically valuable, but every step upward adds assumptions. That distinction is the key to all three worlds. First, 55 Cancri e, a rocky planet pushed almost to the limit. NASA's archive lists it at about 1.875 Earth radii and roughly 8 Earth masses. It completes an orbit in only 0.7365 days, about 17.7 hours. At that distance, the day side is hot enough for rock to be molten and bright in infrared. The simplest picture once sounded brutally clean: an airless lava world with the star blasting away anything volatile. JWST tested that picture with thermal emission. If the day side were a bare, molten surface, it should have appeared hotter. Instead, the measured brightness temperature was around 2800 Kelvin, and the observations included absorption between roughly 4 and 5 micrometers. A volatile-rich secondary atmosphere, potentially containing carbon monoxide, carbon dioxide, or related gases, can explain both the cooler day side and the wavelength-dependent signal. That is a serious atmospheric result, but listen to the wording. The data are consistent with an atmosphere. JWST did not photograph air, and the observations do not uniquely select one gas mixture. Even the idea that magma continually replenishes gases lost to the star is a physical interpretation, not a direct measurement. On the evidence ladder, 55 Cancri e gives us measured thermal brightness, a mismatch with the bare rock baseline, and a plausible atmospheric explanation. It does not yet give us a complete weather report for a lava world. Now move outward to K2-18b, and the evidence changes shape. This planet is about 2.37 Earth radii and roughly 8.9 Earth masses, orbiting a cool red dwarf every 32.94 days. JWST observed it in transmission. Starlight passed through the planet's atmospheric limb before reaching the telescope. The spectrum supports robust detections of methane and carbon dioxide, with little comparable evidence for ammonia. Those molecules are the strong part of the result. Then the story climbs higher. One proposed interpretation places a hydrogen-rich atmosphere above a deep ocean, a so-called Hycean world. The same analysis reported only tentative evidence for dimethyl sulfide, or DMS, a molecule associated mainly with life on Earth. That tentative signal produced enormous headlines. But tentative does not mean confirmed. Its strength depends on instrument reduction, overlapping molecular features, and atmospheric models. Later independent analyses have disputed how strong the feature is, and whether the claimed signal is present at all. Even if DMS were established, context would still matter before calling it biological. And the ocean itself has not been directly detected. Clouds, atmospheric chemistry, and the unknown interior leave multiple non-living configurations open. K2-18b therefore teaches the most important discipline in exoplanet reporting: Do not let the most exciting interpretation erase the more secure measurement beneath it. Methane and carbon dioxide are robust. DMS is tentative and disputed. An ocean is model-dependent. Life is not detected. The result is fascinating precisely because those statements can all be true at once. WSP-39b gives us a different kind of success. It is not remotely Earth-like, about 14.34 Earth radii and around 89 Earth masses, circling its star every 4.06 days. Its hot, puffy atmosphere creates a large transmission signal, making it a powerful laboratory for atmospheric chemistry. JWST clearly identified carbon dioxide and also detected sulfur dioxide. Sulfur dioxide was the surprise, because simple equilibrium chemistry could not make enough of it under the expected conditions. Researchers then used photochemical models. Ultraviolet light can break apart molecules such as water and hydrogen sulfide, creating reactive fragments that rebuild sulfur into sulfur dioxide high in the atmosphere. In other words, the spectrum carries evidence that stellar radiation is actively transforming an alien sky. That mechanism is still inferred through a model, not filmed as a chemical reaction, but it is a tighter chain of evidence than a free-floating story. A measured spectrum contains a clear molecular feature. Standard equilibrium chemistry underproduces it. A reaction network driven by ultraviolet light reproduces it. The atmosphere also shows other constituents and cloud effects, giving the model additional constraints. WSP-39b demonstrates what the upper rungs of the evidence ladder can look like when measurement and mechanism reinforce each other. Put the three planets side by side and a pattern appears. The telescope is the same, but the claims are not interchangeable. For 55 Cancri E, the strongest statement is that the thermal emission is cooler and more structured than a bare molten surface predicts, with a volatile-rich atmosphere providing a plausible explanation. For K2-18b, methane and carbon dioxide are the secure molecular retrievals, while DMS, an ocean, and biology sit progressively higher on the uncertainty ladder. For WSP-39b, carbon dioxide and sulfur dioxide are clear spectral results, and ultraviolet-driven photochemistry is a model-supported mechanism that explains the sulfur dioxide. Size and orbit also matter. These are not three versions of Earth. They are a lava super-Earth, a temperate sub-Neptune, and a hot gas giant. Each presents a different atmospheric geometry, temperature regime, and modeling challenge. The honest comparison is not which one sounds most habitable. It is how far the data allow us to climb. This framework does not make exoplanet science less exciting. It makes the excitement durable. A spectrum can reveal that a bare rock model fails. It can distinguish molecular combinations across light years. It can expose chemistry driven by another star. And sometimes it can identify a possibility, like an ocean or a biosignature, that future observations must attack from several directions. The boundary between measured, retrieved, and interpreted is not a weakness to hide. It is the map for what comes next. More wavelengths can separate overlapping molecules. Repeated observations can test whether a faint feature survives. Better mass, cloud, and interior constraints can eliminate whole families of planetary stories. The greatest discovery may not be one dramatic molecule. It may be learning how to turn a few missing photons into a chain of claims strong enough to trust. Subscribe for the next deep dive, where we keep the wonder and show exactly what the evidence can carry.